Hi, my name is Lavanya Vats and the date today is 19th October 2025.
Hi everyone, I'll be solving the spectral problem N from my organic chemistry lab. The molecular formula given is C6H12O2 and the job is to analyze the IR spectra, the CNMR and the HNMR to understand what exactly the molecule is. So the first step is going to be analyzing what the degree of unsaturation is. I'll go step by step in how I calculated the du, which is the degree of unsaturation, and also how I interpreted the spectra and how everything came together to reveal the final structure that I've drawn from all of the data that we have. Alright, so the very first thing is obviously the degree of unsaturation. This right here, we're going to be using the molecular formula that we have written here. The number of carbon and hydrogen are what we need for the degree of unsaturation. So the formula goes the number of carbons into 2, we add 2 to that, and then we subtract all of this with the number of hydrogen that we have, and finally we divide everything by 2. Alright, so 2 into number of carbon we have are 6, we add that to 2, minus 12 divided by 2, which gives us 14 minus 12 upon 2, which gives us 1, which we have right here. Alright, so the degree of unsaturation we have is 1, which can either mean a double bond or it can mean a ring. Alright, that a ring is present. Since there is oxygen in this formula though, this is probably a carbonyl group, which can be either carboxylic acid or an ester. Alright, now we'll figure out which one it is. Now let's look at our IR spectrum. Right away there's a very strong sharp absorption around this area. Which area? This right here. Okay, this is the strongest one we have in the whole graph, and this comes to about 1700-ish, right? I have a more accurate number right here, which is 1735, and that is basically referring to the C double bonded O functional group, which could be an ester, right? So that hints towards an ester. There's a smaller but a significant band near 1200-ish, which is right here. Or maybe if we go to a particular one, this right here. So this refers to the CO stretch, C bonded to an O. And then, like I said, it was a possibility to have the COOH as the functional group in this. To see if that is the case or not, we are going to be looking around 2500 to 3300. So this place right here does not have any major sharp bands, as we can see. So this means that it does not have a carboxylic acid probably, or an alcohol either, right? So it doesn't have an OH in it, and if it doesn't have an OH somewhere around there, that means COH is probably not the answer. So looking at the IR alone, it is a carbonyl, we know for sure, which is C double bonded to O or CO, but it is not an OH group. Alright, next we are going to look at the carbon 13 NMR spectrum, this one. Now we can see one major signal around 172 ppm, which is referring to C double bonded to O. Alright, again as an ester, carbonyl carbon, right? And then we also have around 60-65 ppm of this signal, which is referring to O bonded to CH2, alright, which is like one in an ethyl ester. Then around 30 ppm, it represents a CH2 group which is close to a C double bonded O, right? And then around 20 and 15, it is basically a middle CH2 which is present in the chain, and then at 15 it's a terminal CH3. So looking at all of this, it shows a distinct 5 or 6 carbon environment, which also matches the molecular formula that we have right here. So these are the datas that I've written for my spectra data table. At around 172 ppm, we have C double bonded to O, which is a carbonyl carbon of an ester. Then at 65 ppm approximately, O bonded to a CH2. Then at 30, we have a CH2, which is close to a C double bonded O. At 20 ppm, it's a middle CH2 present inside the chain. And then at 15 ppm, it's a terminal CH3. Next, we move on to the proton NMR spectrum. This gives us the most detailed story and confirms all of the ideas that we were thinking about while looking at the other spectras, right? So at around 4.1, we're just quickly going to look at the graph first, and then we're going to go through the table, right? So this is one of the places where we have some signal. Then we have this one right here around 2. Then we have these 3 right here between 1 to 2, right? So now I'm going to go to the table and we're going to see what is going on. At 4.1 ppm, the integration is to H and the multiplicity is quartet. Alright, the interpretation for all of this is going to be a CH2 group bonded to an O group. Then we have 2.3 ppm, the integration being to H, and then the multiplicity triplet, CH2 bonded to CO. Then we have 1.6 2H multiplet, CH2 and CH2, a middle chain of CH2. Then we have 1.3 ppm, where we have again 2H integration, and it's also a multiplet, and this is going to be CH2 and CH2 again. So these both are basically the same actually. And then we have 1.2 ppm for CH3 bonded to a CH2 bonded to an O, which is basically talking about a terminal CH3. So approximately the HNMR is also giving us 11 to 12 H, which matches the molecular formula that we were talking about. So all of these data that we see in IR spectra, the CNMR spectra, and the HNMR spectra all show that it is in fact an ester. So first I looked at the IR spectrum, which confirmed that there is an ester functional group. The CNMR structure showed a carbonyl carbon, an oxygen bonded to CH2, and many other aliphatic carbons, right? And the HNMR lastly revealed that an ethyl group is attached to an oxygen, and there is a 4-carbon chain that is attached to the carbonyl. So when I put all of these together, I came up with this structure, which is basically ethyl butanoate, which can also be represented as ethyl butyrate. So this is basically a CH3 attached to a CH2, again a CH2 attached to a C, which is double bonded to O, attached to an O, CH2, and then CH3. Alright, so if I had to draw that structure, it's going to be something like this. CH2, then C double bonded to an O, and then an O again. We have a CH2, and the ending is a CH3. So this is basically the structure that I came up with, looking at all of the spectrums, the observations, and the interpretations I made. Thank you.